I did want to emphasize there are many times when the normal force is not equal to the force of gravity. We showed one when we drew our free body diagrams. When you're pulling a rope upward a little bit, although the object's not moving, the normal force won't be equal to the force of gravity. Notice in this situation right here, the normal force not equal to the force of gravity, which is down here. In this situation, if you're in that a famous amusement park ride, which has made many students sick, but it's very fun, is the rotor where you it's like a spinning cylinder and you feel like you're getting pinned to the wall. The normal force is actually perpendicular to the wall, which is not equal to the force of gravity in the situation. Let's go ahead and do some practice problems. We're going to do the Atwood machine problem. That's a problem like this. You've got let's do it a massless pulley here, no mass. And we've got several objects hanging from the massless pulley. So, and there's a little axis right there. And we've got an M right here, a mass 1. And we've got some bigger masses, or total bigger mass. This is M2. And a big old mass right here, M3. So the question is that we're going to ask in this situation, it's massless pulley for now. Later we'll have to deal with a pulley that does have mass, but for now, massless pulleys. These are ropes, these are masses, and we're going to assume that the sum of M2 and M3 are greater than M1. The questions we're going to ask are, what are the accelerations? What is the acceleration of this system? And what are the tensions? I'm going to use the symbol T for the force of tension. You could use, if you prefer, you could use F sub T for tension. For all the ropes. We want to know for all the ropes. So how do we tackle this problem? This is a complex problem. What the heck is going on? The easiest way I find to deal with this problem is to look at it at first as a system. So what we want to do is actually redraw this so that it's a system. So in other words, another problem is that this is in 2 dimensions, it's going up and down, but if this goes down, that goes up. So which way do we make positive? By making it into a system, we actually make it a lot easier. Before I make it into a single system, though, I do want to draw some of the forces here. I'm going to draw free body diagrams right on this diagram right here. So for M1, what are our forces? Well, we've got force of gravity, M1G pulling down that way. And is there a force pulling up on it? Well, you may say, oh, the normal force. There is no normal force. This is not on a surface. If there is a force up, we'd have to call it the force of tension. I'm going to draw it right here. This is due to that rope. I'm going to call it T1. And this is why I like to use T instead of F sub T, because I won't need double subscripts. That's the tension 1 right there. Now, as long as there's no mass between 2 parts of a rope, we can say for sure that this is also T1. The rope tension will be the same as long as there's no masses in between them, and because our pulley has no mass, we do know that this part of the rope has the same tension. It is not true if the pulley has mass. Those are the same tension. So we've got T1, and so we got these forces on this one. T1, notice that ropes can only pull. T1 is pulling up on this mass 2. Now this is a different free body diagram. I'm showing the free body diagram for M2. We've got T1 pulling up on that. Ropes can only pull. What other forces do I have on M2? Well, I've got the force of gravity pulling on it, M2G. And I also have another force. I've got the force of tension of this rope. I'm going to cut. Now this is a different rope, and this is pulling down on M2. So this is T. I'm actually going to make it a little bit shorter so it allows me to put in some other good stuff. Okay, so this is call that T2. Is it the same as T1? No, it's not, because there is a mass between these two ropes. So this rope's going to have some different amount of tension on it. That is the complete free body diagram for M2. Now let's draw a free body diagram for M3. For M3, we have M3G, big old vector here, M3G. But we also have this T2, but I'm going to draw it up like this. Notice the tensions can only pull on objects. This is also the same T2 because it's the same rope, but it's pulling up on M3. Now this looks impossible. There's so many forces, there's so many different objects. How do we deal with this? What I'm going to do is I'm going to redraw this entire thing as a system. Now, in order to do that, there's a couple tricks you can use. It's so complicated because things are going up and down and all around. It's hard to tell how we could just make this a simple or really one-dimensional problem. This is a one-dimensional problem. They're only moving up and down this way. We can stretch that out into one dimension. So here's how we're going to do it. We're going to redraw it like this. We're going to connect these like so. Here's our M1 connected by a rope to M2, connected by another rope to M3. We're turning this problem sideways. And you might want to indicate in your AP exam is basically we're going to transform this to one dimension. And this will help the grader understand what you're doing. Also, when we're going to look at this as a whole system, this whole mess as one system, what you want to do is you want to draw a little dotted line around it like this. And that is the universal symbol for analyzing this as a system. So we're going to look at this, all the external forces on this system. And what are they? What are the forces acting on the entire system? It's got to be out here. And you may say, well, the tensions are acting on the system. The tensions are not acting on the system because they're inside there. It's as if you had a bunch of if you had a shoebox and you had a bunch of hamsters having a tug of war inside the shoebox, and now of course I'd never do this because it's cruel, but would it affect what the hamsters are doing? Would that affect how hard it is or what the acceleration is when I throw the shoebox? It would not. By the way, never do that. Mean to hamsters. So what's going on inside the box does not affect the overall acceleration of the system of the box and the hamsters. So we only have to be worried about external forces. So let's go ahead and draw those. What are the forces that are external that are acting on a system? And again, I'm going to attach these forces to the whole system because they're acting on the system. I've got M1G pulling this way. Again, I've transformed this to one dimension, pulled it sideways. There's M1G. That's the same thing as this force, but I've just converted it to one dimension, all pulling sideways. What other forces are acting on the system? Well, M2G is in fact acting on the system, and that is pulling it out this way. M2G this way. M2G. Is there any other forces acting on the system? Well, of course, we have M3G. Let's go ahead and draw that in. M3G like this. Those three forces are acting on the system. What about the tensions? We do not have to count the tensions. Why? I mean, if you did, notice that this tension, T1, is pulling this way. T1 would be pulling this way, but T1 would be pulling this one this way. Those, even if you were considering them, they would cancel out on our system because on the system, Newton's third law within the system cancels all those out. In the same way, even if you did try to include this force or this force, they would cancel out. We do not include forces in the system, within the system, because you can't accelerate yourself from within the system. There has to be an external force that acts, and that's all these that we've already listed. So now it's very easy to do a Newton's second law equation that will allow us to figure out the acceleration of the system. That's what we're first trying to do here, is figure out the acceleration. So I want to write Newton's second law, and you always want to write it like this. This is now a one-dimensional problem. It's easy. So net force in the x direction equals max. You first draw your Newton's, you write your Newton's second law equation. Simply as that. Then you get more specific. what are the forces acting on the system? That is, well, we've got, I'm going to make to the left negative. We've got negative M1G. I'm going to try to keep them color-coded. Negative M1G, because it's to the left. I've got positive plus M2G. And I've also got negative positive M3G. Those are both pulling to the right. So notice that I was more specific. This is replacing this side. Now, what am I going to put in for M? This is just a generalized mass. What is the M in this situation? What is the mass of our system? It's the sum of all of these. So our mass is, we're getting more specific again, M1 plus M2 plus M3. That is the mass of the system. And then what I'm trying to find, my unknown that I seek, is A sub x. So you notice when I do this as a system, this becomes easy. All I have to do is divide both sides by this. Divide on this side by M1 plus M2 plus M3. Divide that M1 plus M2 plus M3. And that cancels that. And I'm done. I just solved. This is the acceleration of the system, that whole thing right there. That was easy enough. But now I've got to figure out the tensions. What are the tensions in this thing? So we have to figure these out all separately. What are the tensions? To figure out the tensions, now I have to revert to analyzing the objects individually. So let's figure out what is T1. When you're analyzing object 1, you must realize that the force of gravity on object 2 and the force of gravity on object 3 are not acting on M1. Only the tension is. Again, the concept of contact force is very helpful here, because if these aren't touching it, and we're not even counting the force of gravity these are pulling sideways with on these, it's negligible. The only force on M1 up that way is tension. And that's what we're trying to figure out. So what we do is let's redraw our free body diagram for object 1, which is like this. We've got, and I'm going to now go back to vertical. Let's go back to the vertical so we can look at it that way. So what I have right here is I've got M1. I've got pulling down on it, we've got M1G like that. And pulling up on it, I've got T1. Now T1 should be longer, greater in magnitude than M1G, otherwise it won't accelerate up. So what do we know? Now here's what I'm going to do. I'm going to take this value of AX right here. I'm going to use that. We already solved for it, but I'm not going to use this whole big expression. I'm just going to use AX right here as whatever we found right there. So for this situation, again, I start off with writing Newton's second law. The net force on object 1, I'm going to use object 1 to indicate we're just looking at object 1. And this is, I'm going to leave off the direction. We're in one dimension here, but I'm looking up and down. It doesn't matter. You could keep it sideways if you wish, but then you'd have to analyze this tension. So let's just keep it like this. The net force on 1 is equal to M1 times A1. Notice that the subscripts will always be the same when you're doing this. Then I get more specific. Which way am I going to make positive? Now it's critical that I stick with the sign here. For this problem, I made this way positive. How do I know that? Because I made this negative, M1G, pulling that way. So the way it accelerates is going to be positive. So that means I've got to make M1 positive. So let's stick with that. M1G is going to be positive. I'm just getting more specific. M1G. What's the other force that's acting on this? Only the tension, T1. And that is going to be equal to M1, the mass 1, times its acceleration, which we already know is the same as over here. So this is just AX that I found. Let me go ahead and put that in red because we already got that in red. That's AX that we found from right over here. That's the same thing. We know that. Assuming we know this, the question is what is the tension? All we got to do is just solve for tension. Put that on that side. We just do a little bit of math here. That gives us M1G minus M1AX that we found before equals T1. We just found that tension. Boom, found it. Now, let's figure out what is the tension on one of the other objects. Let's figure out what is T2. What's the tension right there in between these two? That's a little bit tougher. We got to decide which object we want to analyze, M2 or M3. Now, I'll give you a hint. Let's keep things easy. AP Physics is tough enough. Let's keep things as easy as possible. Which one is going to be easier to determine T2 from? Mass 2 or mass 3? Try to take a look at that and figure out for yourself. Which one, I'll give you a hint, which equation would have less terms? Well, you can see that M3 only has 2 forces on it. M2 has 3 forces on it. The tension, gravity, and T1. M3 only has 2 forces on it. We are going to analyze M2, or M3 rather. So here is the way it looks. Here's M3 right here. M3, we've got our force right here that I expressed as M3G in red. So here's M3G. Let's do it in red. M3G is one of the forces. And we also had T2, which I'll do in, let's do it in blue. Here's, this is what we called T2 before. Now, to make this more accurate magnitude-wise, M3G has to be greater, otherwise it would not accelerate downward. So I'm going to emphasize that by making this even shorter here. T2 has to be less than M3G. Big, very common mistake is to assume that whatever this force of gravity is, that's the tension right there. It's not. If it's accelerating down, this has got to be greater than that. I'd say that's one of the most common mistakes, is assuming the tension will be equal to that. The only way it will be equal to that is if this is doing what? It would have to be not accelerating. It would have to be moving down at a constant velocity, moving up at a constant velocity, or sitting still a constant velocity. That's the only time this tension will equal that weight. So once we have this, we already have our givens. We have the acceleration, which is the same thing we had before. We still don't have T2, but here's what we're going to do. We're going to write our Newton's third law equation. Net force on 3 equals M3 times A3, which is just going to be our acceleration that we got before. Same acceleration. How do I know it's the same acceleration? They're all connected. And now I'm going to get more specific. So I rewrite F3. It's going to be M3G. I'm making this positive because a good idea is to always make the direction of acceleration positive unless something's slowing down. Direction of acceleration, usually the best direction to make positive. That's positive, but then I'm going to have minus T2, and that will be equal to M3A. And there we go. Same thing as before. You will just find M3G minus M3A. That will be equal to T2. And there you go. We have now found all the tensions and the acceleration.